All right, so addressing a few other little nuances of the properties of solids. We'll get into addressing a few of the nuances of solids, liquids, and gases next time before we get into full out gas laws. So the learning targets for the properties of solids, and like I said, this is mostly review, a few little added extra things, but we are still looking at the forces and explaining the physical properties. Want to explain the relationship of the macroscopic properties. Explain the particulate level structures or the models. Those are the circle diagrams that show you like on the atomic level. And then explain how those particles interact, what forces are holding them together. Ionic solids, remember, they form these crystal lattices. And I'm just putting the pictures up here to reinforce it's a pattern of positive and negative alternating anion cation pattern. Now the NaF is a 1-to-1, so you see the green purple, that's alternating cation anion. The calcium fluoride example, though, you have 2 fluorides for every 1 calcium in that particular ratio, so the pattern is different, but it still forms a crystalline structure of alternating calcium fluoride ions based off of its ratio. One thing to look at about ionic is the strong interactions tend to have lower vapor pressures, higher melting points, and higher boiling points. Kind of what we were just talking about, it applies to the solids as well. Now the data I included on this slide is to help you evaluate the lattice energies. Remember, the lattice energy, if it's a higher value, definitely means a stronger Coulombic attraction. And that should indicate a higher melting boiling point situation. So yeah, looking over here at our lattice energies of MgO right here, lattice energy 3800 about. If you look over here, it's the one on this particular one that has the highest boiling and melting points. So they definitely correlate over, and that's another reason why ionic solids have high boiling and melting points, because they have really strong Coulombic intra forces, not inter, but intra forces. This is a little nuance that they don't go over in Unit 2, but this is what you need to know about why ionic solids are brittle. The idea of that brittle feature, that brittle property. Because if you hit or apply a stress to an ionic crystal, it ends up shifting the ions. And when it shifts the ions and you have negatives and positives lining up next to each other, they have a tendency to repel. And that causes those cracks, which makes it brittle. So that's a little nuance. You need to be able to read and interpret a diagram like this. That would contribute to the idea of why ionic solids have that brittle property. Another thing, we always talk about how it conducts electricity in the molten or the aqueous stage where it's dissolved in water. We never really talk about why. Well, when we are in these phases and those intra forces, those Coulombic attractions holding the ions together, are now overcome, these ions are free to move, and if they're free to move, they can conduct electricity. So this diagram kind of shows you the solid versus in molten or aqueous. Here they're in locked position, they're being held together by their Coulombic attractions for the solid, but down here the ions are free to move around, and when they're free to move around, then they can conduct the electricity. Covalent network solids, we touched on these briefly. What you need to know is these 4 compounds. That's basically it. And I guess compound isn't the right word for diamond or graphite because they're only containing carbon atoms. But as you can see, they have covalent bonds between them. So the diamond, silicon dioxide, silicon carbide, these 2 are compounds because they have more than one element in them. And then graphite. You need to be able to look at these and be able to explain these 4 examples. So 3-dimensional networks would go for diamond, silicon dioxide, and carbide here. whereas the two-dimensional layers applies to graphite. So graphite has a little bit of a nuance because there's an exception to its hardness due to these like layers here. It kind of has cleavage points. So it is not hard like the diamond or these other two. Of course, all of these covalent network solids are made of non-metals. You have the elemental kinds, which are the diamond graphite. You have the two binary compounds, which are silicon dioxide and silicon carbide. At least they both have silicon in that, so that's easier to remember. But basically, you need to know these four. What else do you need to know about these four? That they have high melting points, really high melting points, because they have these bond angles that are fixed and hard and rigid. The one thing though that you need to remember about graphite is it's soft. It's what we have in our pencils. Why is it? Because those adjacent layers here, okay, can slide past each other. So that part lessens the hardness of the graphite. But it still has a pretty high melting point, way up there, okay, very high melting points, very hard, rigid. You know that about the diamond, though. I'm sure you know that that's one of the hardest substances, on the earth. So keep that in mind. Molecular solids. We didn't go into a whole lot of detail, but we really pretty much have covered molecular now because we talked about IMFs for, the last hour. So molecular solids composed of distinct individual units of covalently bonded molecules attracted through weak intermolecular forces. So these ones are going to have London dispersion type interactions. A lot of them do. They might have some dipole-dipole interactions and things like that as well. The ones in the examples here all happen to be in the nonpolar type category, except for sulfur over here is going to have some lone pairs. But what you're going to see here in terms of the carbon dioxide, the iodine, sulfur, the naphthalene here, which is found in mothballs, it's kind of that stinky stuff to get rid of moths. They all, have weak intermolecular forces. So based off of that idea, they're going to have lower melting and boiling points. And they do not conduct electricity. That's another nuance. We already know that they're poor conductors, non-conductors, because the reason why, though, is those valence electrons are really held tightly in those covalent bonds. So there's no real ability for free movement of electrons here. I also put the melting points on here so you could see that they are considerably lower than anything else that we've seen so far. The much lower melting boiling point situation going on here because of those weak IMFs that hold those solids together. Now, there's not a whole lot of the molecular solids out there. A lot of them are organic molecules too, because they have only carbon, hydrogen, nitrogen, oxygens in them or whatever. But, definitely on the much weaker side here than comparable to ionic, or the covalent network are the super, super strong ones. Ionic are definitely in the super strong category. And then metallic bonding, depending on which metal you're talking about, some of them are really, really strong. Some of them are, kind of in the middle there. Speaking of metallic solids, let's talk about them. They're good conductors, but did we really talk about why they're good conductors? They're good conductors because of those free valence electrons that are delocalized, that can move around. So this figure over here is just showing you how these delocalized electrons, which are the blue circles, when you get an electrical current going, they line up and they flow. The electrons will flow, which conducts the electricity. One other thing to talk about, and last thing I'll end with this, is the malleability and ductility of the metallic solids and why they have these properties. Once again, it has to do with the metal cores, with the free electrons around them. They can be pounded in two different shapes, like sheets for the malleability. Here's the sheets versus the wires for the ductility. You can shape them because of those metal cores can rearrange the structure, those electrons around them. They have the ability to be molded.